Centerville is the headquarters of Grady Cablevision Company. The cable company is about to expand service to 2 nearby towns, and there needs to be cable connecting Centerville to both towns. And the idea is to save on the cost of cable by arranging the cable in a Y-shaped configuration. So then it goes on to explain where the cities are located here using an XY plane. They said imagine that Centerville is located at 90, so that's here. Let's see, Springfield is located at 02, so that's here. And then Shelbyville is located at 0, -2, that's right here. And then the cable runs from Centerville to the x-axis at a point X on the x-axis, x0, and it splits the 2 branches going to Springfield and Shelbyville. So the problem that we need to do is we need to minimize the cable, which will minimize the cost to this cable company. So we want to minimize the total length of this cable. So I called this part of the cable here that I'm highlighting right now, I called that L1, this is L2, and then this part right here is L3. So our function that we find has got to show us the total length of the cable, and then we'll take the derivative and see if we can minimize that. So we're going to take the length of L1 plus the length of L2 plus the length of L3 and add them up. Now, L1 and L2 are the hypotenuse of the right triangle right here. And they're going to be the same length since this comes out to 2 in either direction. So using Pythagorean theorem, we get that this length here, L1 and L2, are both the square root of 4 plus x squared. And then when we find the length of L3, that's the difference between 90 and x0. So I'm just going to take 9 minus x to find that length. So when I combine like terms and clean up the function, I'm calling my function L of x since we're talking about length. I get 2 times the square root, but I changed it into power form to make it easier to take the derivative later. And then plus 9 minus x. So here's our function for the total length of the cable. Now we have to take the derivative. So using the power rule, I'm going to bring the 1/2 down in front, which means this 1/2 times 2 makes that a 1 in front. And then I have 4 plus x squared on the inside raised to the power of -1/2 because we got to subtract the power by 1. And then using the chain rule, we got to multiply by the derivative of what's inside, which would be 2x. When I take the derivative of 9, that's 0 because it's a constant. And then when I take the derivative of -x, I get -1. Then when I clean that up a little bit, I'm going to pull the 2x out in front. So I get my derivative is 2x times 4 plus x squared raised to the power of -1/2 and then subtract 1. Now, to find the critical values, we need to set the derivative equal to 0 and see what values that gives us. So when I set this equal to 0, what's going to happen is, if you notice, this piece right here is raised to the -1/2. So what I did to make it a positive exponent, I wrote it downstairs in the denominator as the square root of 4 plus x squared. Now I'm sure there's different ways to go about doing this, but this is the way that I chose to do it. And then I saw that 2x over the square root of 4 plus x squared has to be 1, so when I subtract 1, I get 0. So this whole thing right here has to be 1. And in order for that to be 1, the top and the bottom have to be equal to each other. So I set these two equal to each other, and then I solved for x. So when I solved for x, I squared both sides. So on this side, I got 4x squared. On this side, the square and the square root undo each other, and I'm left with 4 plus x squared. And then I combine like terms, and I get 3x squared is equal to 4. and then I divided by 3 and took the square root. So actually, I forgot my plus or minus in there. That should be plus or minus. So what we're going to do now, so this is our critical value, plus or minus 2 over the square root of 3. But we want to make sure we're getting a minimum. And what I did, to find a minimum value, you want to take the second derivative and use the concavity test. So I take, here's my first derivative here. I'm going to take the derivative of this function here. Now this we're going to have to use the chain rule and the product rule because I have this right here. So I'm going to use 2x as my first function and 4 plus x squared raised to the negative half as my second function. And between the chain rule and the power rule, this is what we get. All right, so I took the derivative of 2x first, and then I multiply it by the second function, plus, and then I take the first function, which is 2x, and multiply it by the derivative of the second function. Now, when I take the derivative of the second function, I have to remember to multiply by the derivative of what's inside. And then when I clean that all up, and I simplify it, I'll let you guys read through this, these steps on how I simplified it. But what you end up getting when you simplify it is 8 over the square root of 4 plus x squared, all raised to the third power. Now, our critical value is 2 over the square root of 3, and you can check plus or minus, but for me, the plus worked out, okay? So when you plug that into the second derivative, if it's positive, that means it's on an interval that's concave up. If it comes out to be negative, then it's on an interval that's concave down. When I plug in 2 over the square root of 3 into my second derivative, and I put this in decimal form to make it easier when I plug it in, this is what I got. I got 0.6495. which means that this is a positive number, which tells me that that critical value, the 1.1547, or the 2 over the square root of 3, that lies on an interval that is concave up, since the second derivative told me that that's positive. And if it's concave up, that means that that critical value is a minimum. So that's our justification for saying that this value of x, 1.1547, is a minimum. So when we come back here, what does this all mean? That means this value of x right here should be 1.1547. Or you can write it exact as 2 over the square root of 3. And so that's what this value of x needs to be in order to minimize the length of all those cables. And that will save the company some money.